So got one question this morning about the aldol condensates in the organic 2 packets, and the question was, for some of these, are there actually more products than what's listed? The answer is yes. This is kind of one of those like law of unintended consequences that these are meant to be pretty simple problems, and they end up getting like multiple products. So one of the ones I was asked about was this one on page 9. And so we have the aldehyde, and we have 2, 4, 6. 2, 4, 6. And we have the ketone. And the key only talks about the one solution, which is this carbon attacking this carbon. This is 1, 2, 3, 4, 5, 6 carbons. So we would draw, if we had a 1 on 6 attack, we would get the 6-membered ring. When we start counting back, the 2 is going to have the ketone, and this is going to get converted to an alcohol. But the third carbon can also attack, so we can get attack from here. So we'd actually have 1, 2, 3, 4, and we'd end up with a 4-membered ring. And so the first carbon would have this acetyl group, and then we'd have the alcohol. So there's actually 2 answers here. Now, in reality, this is probably going to be the only product you actually isolate, because the 4-membered ring is a lot higher in energy. It's just more sterically hindered than, say, a 6-membered ring. But that said, you're not incorrect to say, like, well, shouldn't there be more than one product? It's like, yes, actually there should be several products associated with this. And the one that kind of gets nightmarish are the last 2. And I can assure you, having written the test, your test is not going to have any questions that's complicated on it. This is 2, 4, 6, 8. So 1, 2, 4, 6, 8. And we've got ketone here and ketone here. And the one beneath it's going to operate in the exact same fashion, so we're just going to talk about this one. So let's say we look at, there's 4 scenarios. So in this scenario, we've got these red carbons attacking. So there are attacks. And then in this one, we've got black carbons attacking. So we have the option of carbon 1 or carbon 2 being attacked. If 1 does the attacking, we have 1, 2, 3, 4, 5, 6-membered ring. And so this will be the first carbon. The ketone's part of the ring, and then we get attack on this ketone, so we get an alcohol. The CH3 group. Make sure you can still see that. Oh yeah, thank you for pointing it out. There's a lot with this. I'm trying to write on it right now, and unfortunately, the desktop version of ACD ChemDraw Lab is being really buggy this morning. So Wednesday will probably be the earliest I get these keys updated. All right, let's say 2 does the attacking. So now we have a 1, 2, 3, 4-membered ring. So there's our 2 carbon. And 2 carbons going to attack. We're going to get an alcohol, and then hanging off this ring is going to be this branch here. So 1, 2. Now, let's say the black carbons attack. Well, the black carbons attack, we have the option of 1 or 2. So if number 1 attacks, we end up with a 4-membered ring. 4. And we're going to get the alcohol and the propyl chain. And then we're going to end up having, since this is the number 1 carbon, we're going to have this acetyl group hanging off. And then if we attack from 2, it'll be another 6-membered ring. I'm going to kind of write it down here beneath it. And we're going to have, since this is the number 2 carbon attacking, we're going to have the ketone, and then it's going to attack that group. And we're going to have the alcohol. And so you get 2 4-membered rings, 2 6-membered rings. And again, the 4-membered rings, you're probably not going to get a lot of by sheer merit of the fact that they're just more sterically hindered. Whereas with the 6-membered rings, those are probably going to be the predominant products. But yes, you actually get both 6-membered rings and both 4-membered rings, because there's nothing to preclude any of these from doing the attacking. And so even with these self-aldol condensation reactions, like they quickly run away into really complicated territory. Again, trying really hard with the test to keep it like pretty simple and straightforward. You'll typically see the book, and to their credit, this is a clever trick. These are typically done with rings, so the rings kind of limit how much the molecule can wrap around on itself. Usually with a 6-membered ring, with 2 groups hanging off, the 2 groups just have to attach. You don't get that many combinations. But yes, I'm currently trying to work on updating the answer key so it has like all the different combinations. And yeah, so it's gonna be a while till I get those posted. Though I do thank you for catching those. So I mentioned in my email back to you, actually the second one on page 9, the key is missing the answer. The second option. This is kind of an embarrassing one. I should have caught this one faster. So this attacking an aldehyde. The nice thing is aldehydes never do the attacking, they're always attacked. So we don't really have to worry about like the different combinations here. And again, you can kind of see where we're trying to cook our answers with this. And so the key only gives this attacking this. But you can also have this attacking it. Alright, so slides 3549, it says because OH is added in the form of alcohol, but instead which was formed under that condition? 3539. Let me bring up the slides. This is usually like an aldol condensate. If it's basic, you mostly get an aldol addition. If you have mixed aldehyde, slide 24. So, on slides going through elimination. $35, $39, $40. It shows that the it says and shows OH hydroxide is added to form the alcohol. So I talk about why it's so hard to get the aldol addition product, and so it says instead. So we had to do something to trigger this reaction. So let's start with just acetone with itself, an isometric. And we want to do a self-attack. And this will give us, as a first pass, the alkoxide. So the question is, how do you even get this reaction going? There is some acidity, but you need basically a base to accept the hydrogen. So if we say, okay, we'll just add a tiny amount of hydroxide, well, the hydroxide is going to pick off the alcohol and pick off the hydrogen, and we're going to end up with the water. So this water is formed as a byproduct of tripping this reaction. This will abstract the hydrogen back off to give you the alcohol, but in pulling the hydrogen back off, now we end up with hydroxide. And so hydroxide here is going to start driving the forward react. It's the hydroxide which started the reaction is going to end up driving the elimination. So in slide 24, it talks about how if you just had acidified water, so let's say you did all this reaction. Let's say you try to do this through acid catalyzed conditions. And under acid catalyzed conditions, you protonate this first. So the lone pair is end up attacking the hydrogen. and then we end up breaking the bond here to give us the enol. I don't want to draw it. I can't remember off the top of my head how you do this. But anyway, so what slide 24 is trying to get at is that okay, I see your confusion because it says this requires an E2 mechanism. The alcohol is the majority product under basic conditions. Okay, I see your confusion. Give me a minute to figure out how to explain it. Honestly, I think that's a typo on slide 24. Now, I understand the point. So I probably got that out of the book when I was writing it. And I understand the point the book is trying to make. So the point the book is trying to make is that if you have any basic alcohol and you try to do elimination with hydroxide, this is actually kind of a hard reaction to drive. Because there is an activation barrier to pulling the hydrogen off with the hydroxide, and the hydroxide isn't the best base. It's got a pKa of about 7, or pKb of about 7. So this tends to be more, it would be wrong to say that, so there's two things here that can create a misconception. Yes, this has to go through E2, and E2 is slow. So kinetically, you could isolate the aldol condensate if you just didn't give the reaction enough time to go. But the favored product is always going to be the elimination. So I would just say slide 24 is not saying it correctly. Like, it's the right idea, but it's not being expressed in the best way. And the best way to express, I would say, and I'll revise the slides for next semester to say this, you're having to do an E2 elimination. So this is kinetically slow. So in principle, this is isolatable. By sheer merit of the fact that this is an E2 pathway, it's going to be slower than an E1. So if you were just to run the reaction and then immediately kill the reaction, you would get the addition product. But given sufficient time, this would be the favored product. So we would consider this the kinetic product. And this is the thermodynamic. And given sufficient reaction time, all aldol additions become aldol condensates. Unless there is like no hydrogen to eliminate on this carbon, they're going to do that. But it's also kind of misleading to say that, well, when you react it, there's no possibility of getting this back out. It is possible to get the addition product back out as long as you're pretty quick about it or you're running over low. Yes, H plus does elimination as well, and this is kind of the challenge with isolating these condensates or these addition products is that if the only way to guarantee that pretty much nothing happens is to run them under neutral conditions. But you either need an acid or a base to catalyze the reaction. So let's say you had an acid. Well, if you have an acid, you would just go through an E1 pathway. And so you start by protonating the alcohol. This would pop off. And then the water would take the hydrogen off. And you would end up basically getting acid catalyzed dehydration of an alcohol. Now, with these H plus pathways, 2 reasons you would want to do it. The base catalyzed pathway for the aldol addition is more more favorable. You end up generating the carbanion a lot easier. The other issue why you wouldn't want to do this is carbocation rearrangement. By going through the E2 pathway, you're pretty much guaranteeing that you don't get rearrangements. But it's going to be kinetically slower, so you have to wait a little bit longer. But definitely if you throw H plus in there, it's just an acid-catalyzed dehydration of an alcohol. So with OH minus, it's just going to have the OH added instead of eliminated. And again, so with OH minus under basic conditions, initially you're going to have the alcohol product. And it's going to be long enough lived that you could isolate it. But given sufficient time, that hydroxide will engage in an E2 mechanism with the aldol just to get the condensate, which is more thermodynamically stable. And unless you're quick to neutralize the reaction, it's going to basically give you nothing but aldol elimination when it's all said and done. And again, I realize it's kind of arguing like two different concepts. It's something I kind of talked about in 251 where there's, so normally with the elimination, the H is going to be removed from the alpha carbon. Yes. Always with elimination, we remove the hydrogen from the alpha carbon. If the alpha carbon doesn't have a hydrogen, then we only end up with the aldol addition product. So if I were to do this compound and hit this aldehyde with it, I would attack here, and I've got this really cooked example to make it work. This can't do elimination if it forms a double bond. Here, carbon would be over octet. So basically, the only reason this doesn't form a condensate is because there's no hydrogen here to remove. There's no incentive to pull the hydrogen off here because the alkene doesn't end up being conjugated with it. So in Chem 251, I don't remember if it was your semester I talked about it, but I had a live stream where I talked about it. And I talked about how the E1, E2, SN1, SN2 is a little misleading. So let's say we run a reaction. And I do elimination, and I get this versus this. So this would be the E2, this would be the E1, and we would do something like tert butoxide. Let's do a halogen here. Tert butoxide and tert butanol. So this should really favor the E2 pathway. Excuse me. But let's say you go out and you conduct the experiment. You say, well, I should be getting the E2, but really this is what I isolate as the E1. So why did I not get a lot of E2 even though my mechanism predicts a lot of E2? And the reason is that even though this is the favored pathway, this is the faster pathway. And so if you take a plot of concentration versus time, and we looked at, so we got time down here. If you looked at the rate of reaction, the rate of reaction for E1, got that one backwards, is higher than the rate for E2. But if we look at the number of times it happens, so the number of times that we do an E2 elimination versus an E1, the E2 will be higher than the E1. So what this is getting at is that this is the more favored reaction, but because this happens so much faster, you can kind of get this false positive where it looks like the E1 pathway happened, was the favored pathway, but it wasn't. It's just that because the E1 goes so fast, it's just more likely to occur. So if you looked at all the atoms, the number of atoms undergoing E2 is, because the other thing to keep in mind is like not all atoms are reacting at once. The reaction doesn't occur instantaneously. So the number of atoms undergoing E2 is higher, but the number of atoms that complete molecules that complete the E1 elimination is higher. So let's say you got a pile of 100 molecules, and the E2 pathway takes 4, but the E1 pathway only takes 1, but the E1 gets done faster. So while the E2 pathway is working on those 4, the E1 pathway is like constantly just popping off little reactions. And so even though you've only got like a small number of molecules undergoing the E1 elimination, it's happening so fast that it makes it look like it's going faster. And I know that's kind of a hard thing to see visually. One other way to look at it, let's say we had a pile of shirts. So we had 100 shirts. And we have 4 people who do like a fancy fold. But it takes like 10 minutes to fold. Whereas we have one person doing a plain fold, it takes them 1 minute. So even though we have 4 people like folding, doing the fancy folds, in the first 10 minutes, the fancy people have only folded 4, whereas the plain has folded 10. And in 20 minutes, these have folded 8, these have folded 20. In 30 minutes, these have folded 12, 30, and so forth. So even though we have more people doing a fancy fold, because they're going so slow, they're not producing as much as the plain folding person who's like cranking it out so fast. So all this to say, this is the addition and this is the elimination. And given enough time, the elimination will eventually do all 100. But as a first pass, the person just doing the plain fold, the addition is going to go really fast relative to it. So we end up forming 2 products, both with the addition and condensation. Yes, so the reason why the packet is set up the way it is that you always go through the addition product first. And then the addition product undergoes a further self-reaction to do the condensation. So the packet makes you do the addition product first, so you know kind of how things add. And then it gets to the condensation part second, and a lot of the condensation products are just the addition products just telling you to do the elimination. So you would always go through the addition first, and then you would say, okay, let's say we gave it more time to react. Or we put it under strongly basic conditions, or we put it under acidic conditions. If it could eliminate, what would it do? Because again, there's situations where you don't have that alpha hydrogen available, so you're not able to do that type of elimination. But all condensates started as addition reactions first, and then they condensed. Yes. We're never going to be really in a situation where you would ever really try to form the addition products. Pretty much always you're going to form the elimination product. Again, it's possible. Honestly, you're probably better just to form the elimination product and then go back and use other reactions to form the addition products. But I would say know what the addition products look like, know how you get the condensation products from them, But as far as the nuances of how you would make those reaction conditions work out to favor addition over condensation, that's kind of, I would push that towards, that's more of a higher level chemistry course. You kind of saw this when you did the aldol condensates last week, this week, this week when you did the aldol condensates. You no, 2 weeks ago because you did your lab reports on it. So with the condensates, like when you ran that reaction, you had 4 products. They were all visible under the UV vis, and only one of them was that weird yellow color. So it's not like, even in the lab, we still have kind of trouble controlling what we're going to be getting out of it. So yeah, I would focus on being able to identify the addition and condensate products. But as far as reaction conditions that make one happen over the other, I think that's more reserved for a higher level course. So last week you worked through an unsymmetric ketones for aldol. If given a ketone that is unsymmetric, why would both sides of the ketone attack to form 2 products? Why would there not be one that's favorable like how it was for elimination substitution reactions? So if you had one like this and it underwent self-reaction, okay, so I get what your question is. So let's say we had this react with itself and we have the option of here or here. So we'd have to consider both possibilities. And so we've got 1, 2, and the question is, why would you have to both to react? Would there be one that's still more favorable? Big picture, yes. One of these is probably much more stable than the others. As far as to, oh, that's why that looked weird. So as far as to which one's more thermodynamically stable, this is something that you wouldn't be able to figure off the top of your head. Probably people who do the work probably have some intuition with it. We don't focus on which one here is going to be the favorite product overall. The reason being is like it's just not that easy to work out in your head. So I guess the short answer to your question is we considered all possibilities because we don't have reasons to eliminate them as answers. So for the question you asked me about with the 2 different products being formed, one was a 6-membered, one was a 4-membered, you're probably not going to get a lot of the 4-membered ring, but that doesn't discount it as a possibility because cyclobenzene, cyclopropane, or cyclobutane does exist. Like, it's not impossible to make these molecules. So, and I'm working on right now where it's like, okay, well, if you make the cyclobutane and you do the elimination, now you have cyclobutene. That's definitely higher in energy. But again, there's nothing precluding this from happening. Like, you're not forming something that's objectively super high in energy and shouldn't exist. You can make arguments for which one will be the majority product. But again, we're going to kind of stay away from that because it does get a little nuanced as to how you figure that out. So right now we're just considering what the possibilities are. We can consider in a higher course like what the likely possibilities are. Because the other thing that's kind of missing, and you'll see this in the key, is that there's also both the cis and transforms of a lot of these aldol condensates, and simply just don't write them out. And the reason I'm not writing them out is like if you considered all the EZs, all the RSs, it's too much. Glycosylated issue would not work for something like HCl. The big reason you need the NOH is you need the carbanion. So this is also just a particularly stubborn reaction to run. So with haloform, we need the hydroxide to form the carbanion to begin with. And this sets off the reaction. For acid catalyzed conditions, let's cheat and look at the notes. How do you do this under acid catalyzed conditions? I mean, part of it is that you're forming a primary carbanion, so those aren't particularly favored, and so you need something pretty aggressive like a hydroxide to make that happen. I think the other issue is simply just charge balance. So if you were to go through an analogous H plus reaction, you have an excess of positive charges, and when you do the haloform, you have to end up with these X minuses, these halide anions. So if you got the H plus, I don't think you got a good way to here to get the like the chlorides, the bromides, and the iodides. So I think the hydroxide serves two purposes. One, this isn't as acidic as something like secondary or tertiary would be. So you do kind of need the aggressiveness of the hydroxide. I don't think the H plus is going to give you enough kick to really drive this reaction. And the second is that with hydroxide, we're inherently starting with a lot more negative charge. And we need to finish with negative charge in order to get the haloform reaction to work. So we have to form halides. There is no halide equivalent of a positive ion. So there's no halide cations. So that would be kind of my hand wavy explanation. Is like I think it's the acidity, the hydrogens, and just how the charges work out. Slide 7. So if, okay, I'll make sure we're reading your question right. Both R and R prime are alpha carbons, which would be more before. Would there be a halogen, would the halogen attach to them? So no, so it wouldn't work for aldehydes. The big thing is that you need something that puts enough charge. So you couldn't do hydrogen because the aldehydes, I want to say this. Your alkyl groups stabilize that. Okay, one question at a time. R and R prime were both alpha carbons, which would be more preferred. Where would the halogen attach to them? So I guess what you're asking is, let's say we had two alpha carbons next to the ketone. And we want to know if there's a preference for these, assuming R and R prime are not the same thing. So first question is, are these two the same? So if they're both CH2s, then we have to look at the R primes. But let's say this one is a tertiary versus a secondary. This will be the first to react because you end up forming a tertiary. No matter what mechanism you look at, you end up forming a tertiary anion or cation. That's far more likely to react. Now, in terms of R prime and R, what you're looking for here, let's see here. We're looking at acidity. So if R prime is more electron withdrawing, so we have things like fluorides or nitro groups, the more electron withdrawing these R groups are, the more they favor the acidity of the hydrogen. So if this was like an NO2 group, or this was like a trifluoromethane, this is going to react before this does by sheer merit of just being more acidic. Now, back to the haloform. So we need just the ketones that don't have any hydrogens. And part of this is just by sheer merit of what we're going to finish with. So at the end of the day, when you do the haloform reaction, you end up with a carboxylic acid. And this carbon here becomes stabilized by whatever this R group is. So if this R group is very electron donating, this ends up being a fairly stable carboxylic acid. But hydrogen is not really good enough to stabilize this type of acid. And I forget what this is called. But this is actually a very hard acid to synthesize by sheer merit of the fact that this carbon has so many electron withdrawing groups around it, it just really doesn't want to exist. So we can't even, you can think of this as like CO2 that's been hydrogenated. We can't even make this reaction go. So you can't have an aldehyde because if this were an H group, your final carboxylic acid simply would not be stabilized. You're pulling too much electron density away from that carbon to stabilize the molecule. So again, yeah, it would just have to be the ketones where the R group doesn't have hydrogens. enol versus the example on slide 4, which enol would be more stable or favorable? Slide 4. Oh, definitely the 100% the phenol, because the phenol is aromatic. This compound here on slide 4, it's a cyclic. The example it's being referred to, you can form this enol. But this is an aromatic. So if you compare this to phenol, phenol is aromatic, and in order to make the ketone, you'd have to break the aromaticity. So if there was a way to make this aromatic, in principle you could, but under the restrictions under Lewis theory, this is not aromatic. So 100% phenol is way more stable. Boy, I did myself any favor on that example. When referring to alpha carbon and there are no hydrogens, is it still classified as alphas next to the C carbonyl? Yes. Is it referring to the carbons next to the carbonyl, or do those have to have available hydrogens? So the alpha carbon is always the one that's adjacent to the carbonyl, and it just follows the pattern: alpha, then beta, delta, gamma, epsilon. I have seen books go off to infinity. Well, I guess they can go to infinity. There's only 24 Greek letters. They can go off for quite a ways, particularly when they start describing carboxylic acids. But yes, it's all, alpha carbon's always adjacent to the carbonyl, followed by the beta, followed by the gamma, followed by the delta. For alpha, beta, delta, gamma. Oh, alpha, beta, delta, gamma. With halogenation reaction, how do we normally know only one or two hydrogens be added? It'll be the stoichiometry. So if you see like a half Cl2 or half Br2, that indicates that you're only adding one. The excess, and I'll try to provide numbers if I want so many. But so if it's addition to a, so there's examples in the packets where it talks about the enol versus ketone forms. With those, you're adding one equivalent. So for the double bond, you should get addition to both sides of the double bond. But if you're doing something like alpha elimination, so you're replacing like one of these hydrogens, if you see like a half Br2, that just means add one Br. If you see Br2, means add two Brs. Because those reactions technically just go until they're out of hydrogens to replace. And we're going to pretend we have that type of control over the reaction. Page 7, problem 2. How would you know that Cl goes where the OH is located for the enol product? The key shows that, but why was Cl not positioned next to the methyl group if it's tertiary? Actually, that's probably a case where you get both. So I would definitely argue it goes to the carbonyl more light as a more preferred product. So if you look at the enol product, and we want to add HCl, odds are you probably actually get both. You would get an addition to there, as well as to the tertiary. I would argue this is the more favored product by merit of the charge on the carbon. So your chloride here is the anion. This is going to be more positive than this because this has the oxygen attack to it. So I think this is the more favorable product. But that said, I agree with you that these are actually both tertiary carbons when you work it out. So all things being equal, so ignoring that it's an OH group, it's probably going to do both. Same page, problem 1, the ketone. I was thinking the bromine can attach to where the CH3 group is, but the key shows it's not a reaction there. Again, like I think it's kind of this, well, if it's Br, it should be adding to both. So the ketone product shouldn't do anything, it's the enol. Got the key up. So page 7, the first one, it does show bromine on both positions. So for the Br2, it has to add across the double bond. So when you've got your enol, we had to have, for Br2, it's just across, it's to both carbons. There is trans stereochemistry here. We are not going to bother with it at this point. But yeah, I'd agree with that because it's just bromine addition across the double bond. ketone one, there's no reaction. Yes, there is no reaction with a ketone. So with this, unless you have light, so if you had light, you could make the argument that it would do halogenation. So I would agree with that, but we don't have light. And the bromine can't add across this carbon-oxygen double bond. The oxygen-bromine bond just isn't favorable. So for this bromine, we're only doing addition reactions. We're not doing substitution reactions. So I think that's what you're asking more is like, well, can it substitute there? And yes, if you had light, it could do that. But we're just doing Br2 addition. Adding it to the alpha carbon. And I think I know what slide you're referring to. See your point, because on the second slide it does talk about how... Okay, I agree with you. The key needs to be changed. You're correct. This is an acidic hydrogen, so it should just pop right off. And we should get an anion, and you should get that. Yeah, you're right. I agree with you. Something else to add to the key changes. Let's see if that happens anywhere else. Nope. 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 I guess you could argue that one, but we're going to go with you're overthinking the problem if you're going to argue that one. You know what? I'll put that in the answer key just to mess with people. How about this one? Aldol and condensation of these just cis trans or just the trans product. Even your textbook concedes you should be drawing cis products as well, but one, they're probably not likely to form, and two, it's just way too much. Should I just copy and paste it? Boy, I think I finally corrected all the issues with the packets this time. Why does a double bond attack the ketone instead of the hydroxide? It's more about what you're forming. So double bond attack the ketone instead of the alkoxide. So why doesn't that occur? But that does. It more just has to do with the stability of the bonds formed. Carbon-carbon coupling is a lot more stable than carbon-oxygen coupling. So I think it's more just kind of driven by thermodynamics. There's probably also nuances with this that like the double bonds will line up their p orbitals when they attack. So if I kind of draw this on edge, I've got my hydroxide, I've got my alkoxide. These p orbitals sit above and below the bonds. And so they probably have an intermediate where they overlap their p orbitals first, and then that forms the bond. Whereas this is just a straight sigma attack on the double bond. So my guess is twofold. One, the carbon-carbon bonds are stronger. And two, in terms of the actual mechanism, there's probably a lot more going on here with the pi bond overlap that makes this more favorable than just having a nucleophilic attack. And then when forming, we abstract the hydrogen that is not on the most substituted carbon. You generally will abstract the hydrogen from the more substituted carbon. Yeah, so it's on the most substituted carbon because you are forming a carbanion, and the carbanions are more stable on the more substituted carbons. All right, you're welcome. Thank you for asking them. It's actually good to find somebody who's catching a lot of these things in the keys. Which makes me a little concerned because these keys were used last year and no one caught this. All right, I will see you tomorrow. Got a couple minutes left. And that's it. So again, thanks for showing up to the live stream. Always good to have questions. Also good to get feedback on these packets, particularly because these are harder materials. So even as an instructor, it gets hard to kind of catch this stuff. So I will see some of you for lab tomorrow and live stream Thursday. See you tomorrow.